1995, University of New Hampshire at Durham. Recorded for Radio Free Maine by Roger Leisner. We now join Mary Clark as she introduces Noam Chomsky.
Linguistics at MIT, a man who has been described in the New York Times as, quote, arguably the most important intellectual alive today. Professor Chomsky has some very interesting things to say about political issues, as you'll learn if you come to his second lecture this afternoon at 4 o'clock. But in this lecture, he's going to talk about linguistics, which is his primary scholarly field. In fact, the field of linguistics has been completely transformed by his work of the past 40 years. Professor Chomsky's first book, Syntactic Structures, was published in 1957. In this book, he posed a new and very ambitious question. What do we know when we know the English language? Of course, scholars had been studying language for a long time and had developed an extensive terminology for talking about parts of speech, grammatical functions such as subject and object, and so forth. But what Chomsky did that was new was to set out a detailed formal system that tried to mimic the ability of English speakers to generate all and only grammatical sentences of English. This was, of course, a project that could never completely succeed. But in attempting to carry it out, Chomsky developed very important insights that opened the way to even more interesting and ambitious questions. The grammar he set out in Syntactic Structures made use primarily of two sorts of rules. Phrase structure rules, which describe how words are put together to form phrases, and transformations, which describe the movement of constituents out of their normal positions. So, for example, when we ask a question such as, "What can you see?" the question word "what" appears at the beginning of the sentence, even though it stands for the direct object of the verb, and direct objects in English normally follow the verb. I can see the blackboard. This illustrates a transformational rule of English called WH fronting that takes a questioned element out of its normal position in the sentence and moves it up to the front. Chomsky and his students soon observed, however, that a questioned element cannot be pulled out of just any position in a sentence. So to use an example of Chomsky's, paralleling the statement, "They kept the car in the garage," we can form the question, which garage did they keep the car in? But given the statement, "They kept the car that was in the garage," we cannot form the question, which garage did they keep the car that was in? In other words, there are constraints on the circumstances in which the rule of WH fronting can apply. And similar constraints have been found to hold for other sorts of rules. In fact, as investigation proceeded, the constraints began to assume greater importance than the rules themselves. If the constraints are stated precisely enough, then the rules themselves can be very vague and general. Move something. The constraints and other principles then tell us what can move or must move and where it should move to. But since these constraints and principles are very abstract in nature, and there is no direct evidence for them in the surface form of a sentence, another question inevitably arises, namely, how do we learn these constraints and principles? Chomsky's answer is that, for the most part, we don't learn them. Constraints or principles of this sort are not something we learn. They are part of what we bring to the task of learning. They are part of the human faculty for language. Thus, Chomsky's original question, "What are the properties of a grammatical sentence of English?" begins to give way to more interesting and even more ambitious questions, such as, what do human beings bring to the task of learning a language? And what is a possible human language? In other words, what properties does a language have to have in order to be learnable by a human child? Chomsky himself continues to lead the investigation of these questions. During the course of his career, he has published some 15 books on linguistic theory, and I didn't try to count the number of important and influential articles. Linguists all over the world now work in the framework that he developed. And because Chomsky's work has important implications for the general study of the human mind, he has also had enormous influence in the fields of philosophy, psychology, and cognitive science. He is indeed one of the great thinkers of our time, and I'm very proud to introduce Professor Noam Chomsky. The title of his talk is Current Issues in Linguistics and Philosophy.
Okay. How's that? Can you hear me? Yeah? Okay. Nice when technology works. Rarely happens. Well, you actually heard a rather good talk, I think, about what linguistics is about. So that's a lot of things I don't have to talk about. What I would like to do is to try to give some of the flavor of the sort of work that's going on now in areas that, at least to my judgment, are the most exciting and most important. Others, no doubt, feel otherwise. But I'll talk about what I want to. I'm not going to be able to discuss it in any detail, but I'd like to see if I can try to give a sense of what it's about, what kinds of questions are coming up, and what sorts of questions still aren't coming up because they look impossible, which is an interesting distinction, and other things of that sort. However, to make any sense out of this, it's necessary, as far as I can see, to think about where it came from. And I know I'm constantly rethinking where it came from, as in the other sciences. You begin to understand what was happening a long time ago the more you get to know. So people do Newtonian physics today quite differently they talk about Newtonian physics in history of science quite differently than they did, say, 50 years ago, because new things are understood, which makes the questions look different and the intuitions different and so on. And the same is true in this corner of the sciences. So questions look different that were asked.
They're asking for a little more volume in the back.
Yeah. How's that? Can you hear me? In the back? Yeah? Okay. Is that all right? Yeah, if it isn't, yell or something. Yeah. I'll try to keep my eyes up there. I was just saying that I want to, if you didn't hear what I was saying before, I'm going to try to give something of the flavor of current work, but against a background of some partial reinterpretation of where it came from, since things tend to look different as you understand the problems differently. As was mentioned, this direction in the study of language and the study of mind altogether took on a sort of a pretty new course after the Second World War. Actually, to be more accurate, it returned to an old course that had been forgotten, completely forgotten, and approached it from another point of view, which hadn't really been possible before. That's, again, something not at all uncommon in the history of science. So, say, take major moments. Newton believed in transmutation, as you know, and spent most of his life on alchemy. And he had good reasons for that. It wasn't silly. The reasons were the basic assumption that the world was all constructed out of, everything in the world was constructed out of little tiny invisible objects, corpuscles, that were the building blocks, and anything could be made from anything else, from those blocks. So you could make, just as with bricks, you can make one building, or the same bricks, you can make a different building. With these things, you could make water, or you could make a tree, and so on and so forth. And in fact, they even had experimental evidence that water could be turned into a tree. So the origins of chemistry come from an experiment falsely demonstrating that fact, but rather convincingly demonstrating it. In fact, it wasn't for a century and a half that people found out what was wrong with the experiment. But so here is an idea that says every entity in the world is constructed from the same things, and therefore if you rearrange them, you can turn anything into anything else. That was finally abandoned around about 1800 or so, with the conception of elements that you study in chemistry. So sodium is different from iron. But of course, in the 20th century, it's been revived. So there's a certain sense in which, indeed, everything is constructed from the same things, and in which, indeed, the sense in which transmutation is indeed possible, at least in principle and maybe even in fact. But this is another, I mean, that's a huge case. This is a small case where some of the earlier ideas, which were abandoned because they seemed completely unfeasible or crazy, have been revived and, in fact, turn out to be pretty sensible if looked at from a different point of view. The traditional idea that was sort of in the air and occasionally articulated over the years from about 17th century on until it died in the early 20th century was captured in a slogan of one famous linguist, Wilhelm von Humboldt, that language involves infinite use of finite means. In short, the brain is finite, plainly, but you can make infinite use of whatever resources it has. Infinite just means you can keep going on and on with new objects without any limit. And that part is true. It does involve infinite use of finite means. That was an aspect of an observation that led to the classical theory of mind and body. Earlier, Descartes had based his conception of two different substances, mind and body, on the fact that humans uniquely had this capacity to make infinite use of finite means in the use of language, whereas he argued no automaton could do this, and no other organism could do it, so there's got to be some fundamental divide between humans who have a mind and other organisms and automata and so on that don't. In fact, that is the classic mind-body problem. This notion goes on. Efforts to deal with this problem remained and continued for years. Maybe the last representative of this tradition is Otto Jespersen, an important linguist of the early part of this century, who has an interesting book which people are starting to read again. They didn't read for a long time, called Philosophy of Grammar. It came out in 1924, which is sort of the last theoretical exposition of this point of view, in which he said the task of the linguist, he said every person develops in their mind somehow what he called a notion of structure for their language. And that notion of structure guides them in constructing free expressions. Free expressions are typically novel expressions that you say in an appropriate circumstance and that other people somehow understand, even if they've never heard it before or anything like it before. And you can do this without limit. And then he said, well, the task of the linguist is to figure out what the notion of structure is and how free expressions are constructed for it, and furthermore to figure out how that notion of structure gets into the mind of the speaker, of the person who knows the language, given just exposure to various kind of chaotic and actually pretty limited experience. Those are indeed the problems. They remain the problems. Some of them, and they were pretty much forgotten. They were dropped by the early part of this century as the study of language and anthropology and psychology went off in a different direction, a direction that was considered much more scientific. The scientific direction, as most science does, and correctly, narrowed the scope. It narrowed the scope to particular things. Well, sometimes that move is the right move. Sometimes it's the wrong move. You never know until you see what happens. So when Galileo restricted the study of motion to things like balls rolling down inclined planes, he was ridiculed because things like that don't happen in the world. And besides, what about all those other things like flowers growing and people perceiving things and so on and so forth? But that turned out to be the right narrowing. Out of it came a lot of understanding. Often the narrowing doesn't turn out to be the right one, and I think this was one of those cases. The linguistics and anthropology and psychology from the early part of this century focused on things that they could pretty much observe, on arrangements of sounds, maybe arrangements of words. What you discovered very quickly, there was a great expansion of the range of materials that were looked at. So people began studying widely different languages that they'd never looked at before. And it looked as if, well, a standard slogan in the mid-1950s was, languages can vary arbitrarily in every possible way. Any array of sounds and words could be a language. There's no limits. How do you acquire language? Well, the general assumption was it's just a habit. You do it by rote, the way you sort of walk across the street or something like that. And in fact, the big problem about the 1950s for language acquisition was why it takes so long. It was a problem called overlearning. Since it's so trivial, how come it takes a child years and years before they can do this elementary thing when they can, sort of walk across the room very fast? So the problem is, overlearning. Notice it's the exact opposite of, say, Jespersen or Descartes' problem, how you get infinite knowledge. And this was all in the behaviorist tradition and so on and so forth. One aspect of this was European structuralism, which has very little impact in linguistics, but had huge impact on other disciplines, literature, anthropology, and so on. It was concerned with the patterns of sounds and the way they interacted with one another, and so on and so forth. Again, a very strict narrowing of attention, which was not without results, but turns out to really miss most of the important questions, like the questions that were asked up through, say, Jespersen. After the Second World War, there was another approach that suddenly came along. That was a kind of a high-tech approach that came out of the new technology, and computers were just coming along, artificial intelligence was coming along, information theory had just been invented. And out of this, there was a lot of euphoria about what's going to come out of, new technology and understand mathematics and so on. And it was, in fact, generally assumed. When I take this book, Syntactic Structures, that was mentioned. If you look at it, you'll notice that the first part of it is devoted to an argument showing that the theory of automata and information theory and all this sort of thing can't do anything. They have nothing to do with language. The reason why it's there is because what was thought at the time, this was undergraduate course notes at MIT, engineers and scientists, and it was always assumed at the time that this is the answer to everything. The sophisticated psychologists assumed that, the engineers assumed that, mathematicians did, and it was just, that was clear enough so you could disprove it very quickly. It's one of the advantages of being clear. Other things were vaguer and harder to disprove, like, say, behaviorist psychology, which had even less merit, in my opinion. But so there were, around the 1950s, there was structural linguistics in its various varieties. There was the sort of high-tech approach, and the tradition had pretty much been forgotten. But of course, it remained in the schools. So, for example, when you study traditional grammar, you are studying the empirical side of the old tradition. If you're studying, say, a second language, say you study Spanish, and they teach you, how to make sentences and so on, that's the empirical side of the old tradition. And in fact, it was assumed by traditional grammarians. Jespersen was a major traditional grammarian, and he and others assumed that they were indeed giving a comprehensive account of the language. So it was generally assumed that if you read if you had the time to read a 10-volume grammar of English or Spanish or something, you would know the language. It was also assumed in parallel that if you looked at a dictionary, say the Oxford English Dictionary, the one you look at with a magnifying glass, you could find the meaning of a word. So you want to know the meaning of the word river, or tree, or city, or desk, or something, or some more complicated one. Look it up in the dictionary, and it'll tell you. It was also assumed that the dictionary is comprehensive and that indeed the grammars are comprehensive. Well, both of those beliefs turn out to be totally false. The dictionary tells you almost nothing. The only reason why we can use dictionaries is because we already know the answers. And the dictionary gives you just enough hints about what you couldn't know so that using the knowledge you already had, you can build up the rich concept that in fact goes along with the word. And very much exactly the same is true of the structure of sentences. The examples you heard are perfectly typical. People thought they knew how to form questions because there was a rule there in the traditional grammar that said, move the question word to the front. But as soon as you began to look, it turned out that what people knew about forming questions was something completely different. And you could show that easily by experiment, and it ramifies all over the place. And in fact, none of the rules that are presented in traditional grammars come even close to describing the phenomenon. But they're very useful. They give hints to people about things that they couldn't know, idiosyncrasies of a language that you can't know, the kind of things that a child would have to learn. And then the person who has all the intuitive knowledge somehow stored in there can figure out the rest. So the example that was, let's just take the example that was given, forming questions by taking a question word like what or who and putting it in the front. Well, that is something that a child can't know about the language that is being presented, because languages just differ in that respect. Some put it in front, some don't put it in front. They just leave it there. And there's no way of knowing that. That's arbitrary. That's like not knowing whether tree is going to be pronounced tree or bound. There's no way of knowing that, so you have to hear it, and then you know. Similarly, you have to hear that the language you're being exposed to is one that moves question words to the front, so you know you're speaking English and not Chinese or Japanese, which leave them down, you know, where you interpret them. Interestingly, well, I'll come back to this. But so that's a respect in which languages just differ. So, of course, the grammar has to tell you that, just as information from the outside world has to tell the child that. But all this other business, you know, like why you're not allowed to say, you know, whatever the example was, you found the car that was in, what did you find the car that was in? That kind of thing, yeah, sure. That you know already because you're a human being. And it's part of the nature of a human being to have that kind of knowledge, which turns out to be a very interesting kind of knowledge. Same is true about dictionaries. So, I don't know, take any word you like, it doesn't matter. Take, say, river, since I mentioned it. There's a thing that flows by my office called the Charles River. If you look up the definition of river in a dictionary, it'll tell you something. In fact, it'll tell you enough for a speaker of Spanish to figure out what river means in English. On the other hand, it won't tell you what river means. That you have to bring to the dictionary. And you can easily test that for yourself by simply asking questions like, when would it, under what conditions would a modification of the Charles River still be the Charles River? How do you, what's technically called, individuate rivers? What are the properties that make two things the same river, let's say? Well, it can't be the same molecules because they're flowing, they're always different, so it's obviously not that. Is it the fact that it follows a particular course? Well, it can't possibly be that, because if the Charles River was rerouted, let's say around MIT, because they wanted to build a road, it would still be the Charles River, right? Under some conditions, not all conditions, but under some conditions it would still be the Charles River. Suppose it was rerouted so that it didn't even go out to the sea, like suppose it ended up in one of the lakes near Cambridge because, you know, they wanted to build a reservoir or something. Well, that would still be the Charles River, although its flow is completely different now. It doesn't even go into the sea. Suppose they decided to reverse the course of it. That's happened, not here, but as far as I know, but it happened in the Soviet Union. One of their massive, you know, destructive projects was to reverse the flow of a major river. Well, it was still the same river, you know, even though the water was going the opposite direction. Does it matter what's in it? Well, to a certain extent, but not too much. I mean, I'd hate to think what the Charles consists of. You probably, if you fell into it, you wouldn't survive very long. But it's still the Charles River. I was in Pisa a couple of years ago, and there's a thing that flows through Pisa, which is still called the Arno River, which is some kind of yellow mixture of chemicals from upstream somewhere. It may have a little bit of H2O in it still, I don't know. But it's still the Arno. And in fact, you could do all of these things at once and keep the same river. You could, maybe it's 100% chemicals now. That was 15 years ago. It was probably only 90% chemicals. But suppose that it turns out to be 100% chemicals, 0 H2O. The course is changed completely and, in fact, reversed. It could still, under certain circumstances, narrow circumstances, in fact, be the same river. So whatever our concept of river is, it has all these properties. And incidentally, the same is true of things like water inside the river. There's a common belief, in fact, it pretty much dominates contemporary philosophy of language and philosophy of mind, and it's like a dogma, that water is H2O, that's the meaning of the word water, that water, more technically, is in our minds something which has the same essence as this particular thing over here. And same essence is something that science tells you, and it tells you it's H2O. Well, that can't possibly be even close to true. Whatever water means, it's not that. And we know it very well when you start. You're not going to find this out from the dictionary, but you know it as soon as you start thinking about it. So let's imagine, for example, that we have pure H2O in a cup over here. Okay, pure H2O. Well, that's obviously water. Although, incidentally, when you ask people, they in experiments, they estimate that in pure H2O, they say it's only 98% water. I don't know why, but that's the judgment people give. But so anyhow, pure H2O is pretty close to water, let's say. Suppose that you take a tea bag and you put it in the water, and it slightly changes the content. So if a chemist looks at it, he would say it's a little different. Well, that's not water anymore. That's tea. If you ask for a cup of tea and somebody gives you water, you get mad. And if you ask for a cup of water and somebody gives you tea, you get mad. That's not what you asked for. So this thing isn't water anymore. It's tea. All right, now let's imagine another circumstance. Suppose some, biologist comes along and figures out that tea happens to be a terrific way of removing bacteria from water. And they decide to build, instead of putting chlorine in the reservoir, they put in a tea filter. Okay, so the water goes through the tea filter and comes out your tap. And let's imagine that I got another cup here, which is pure H2O that went through a tea filter from the reservoir. Well, what's that? Well, that's water, just like the stuff that's coming out of the tap now is water. Even if a chemist couldn't tell the difference between the two cups, one of them H2O with a tea bag dumped in it, and one, the stuff coming out of the tap, which happened to pass through a tea filter, we know the difference. One, though they're physically identical, even molecule by molecule identical, one is tea and one is water. So whatever water is, it's not a substance. It's something that it's a mental construct of some kind. That's true of names as well. Remember the Charles River. The Charles River is a name, and in fact every name is like that. It's some complicated mental construct. Well, without pursuing it any further, these are things that everybody knows. Nobody's taught. If you tried to teach anybody these things, first of all, we wouldn't even know what to teach them because nobody knows. These questions are barely beginning to be studied. But certainly no child has ever taught it. If you tried to teach anybody, you would just confuse them. They try to teach a child these things about tea or water, they get totally confused. And the same is true and that's true of every word of the language, and it's true of every sentence of the language. If you tried to teach people studying English, say Spanish-speaking people, if say you take a course in Spanish, and they tried to teach you the way questions are actually formed in Spanish, all these things about when you can move the word and when you can't move it and so on, you would be completely confused. You'd never figure it out. On the other hand, if they just tell you, well, move it to the front, then you know all the answers because you're a human being and you've got all the answers built in. So the fact of the matter is that the comprehensive dictionaries and the comprehensive grammars presuppose everything that we're trying to figure out. They don't answer the questions, they just presuppose the answers to the questions. They're basically presupposing human intelligence. And if you want to know what human intelligence was, well, nice to know what's presupposed, but that's the question I'd like to answer. So traditional comprehensive grammar was saying lots of interesting things about expressions, but it was saying pretty much what is not interesting for somebody who wants to know what the human mind is like or what the language faculty is like, because it's presupposing all of that unconsciously. Science really begins very typically when you get the ability to be puzzled by extremely simple things. Like if it seems obvious that an apple's falling to the ground because, where else should it go? That's its natural place. You don't get physics. It's only when you get puzzled about the fact that the apple's falling to the ground instead of flying up, or that things hold together instead of flying all over the place, or for that matter, the opposite, that all the matter in the universe doesn't converge into a single point since there's attraction. It's only when you get puzzled by simple things like that that interesting questions arise and you try to find answers, and that's what happened about 50 years ago, 50 years ago. For the first time, people started being puzzled about things that look obvious, and as soon as you looked at them, they were anything but obvious, and it turned out there were some quite complicated and intricate answers. Well, that was the atmosphere about 1950. It was possible there was an effort to pick up again the traditional questions, but from the start, nobody even knew that they had been asked before. Everything had been forgotten. There was like a gap in understanding. It's only later that people began to discover what had been said before. Well, why did it become possible to ask these questions around 1950, but not, say, 50 years earlier, or 200 years earlier? The answer is that there had been some new discoveries in the formal sciences, in mathematics and so on, that clarified the concept of infinite use of finite means. That looked very mysterious before that. How could you have infinite use of finite means? But a partial answer, I stress partial answer to that, came out in mathematics and what came to be called the theory of automata, or the theory of algorithms, or the theory of computing, and so on, with Gödel and Church and Turing and others. A concept of computability was produced that answered some of these questions. It made it possible to understand how a finite system can have can express an infinite number of things. And there was a very clear concept by 1950. In fact, there seemed to be an absolute notion of computability, such that every way you tried to approach it, you always came down to the same concept. And that was common knowledge by that time. And that made it possible to re-ask the old questions from start. Now you could ask something about how you form free expressions with a finite mind, or how you can make infinite use of finite means. But here you have to be a little cautious, because it's only one aspect of that traditional question that could be faced. The question that Descartes and Jespersen and Humboldt and others were asking was a question about how you speak. How do I do what I'm doing now? What I'm doing now is forming new expressions, and you're hearing new expressions. So how do we do that? It was a question about performance. And here's where the questions of mind came up, the fundamental questions of mind. The question that Descartes asked is, how can a person, though not a parrot or an automaton presumably, how can a person produce new expressions which are not caused by the circumstances? So you're not forced to produce that by your inner state, let's say, or the things around you. But even though they're not caused by the circumstances, internal and external, are nevertheless appropriate to the circumstances. That's the crucial issue. How do you continually do new things that are that are not caused but are appropriate and are coherent, and that other people understand as coherent and appropriate, and that evoke thoughts in the hearer that the hearer could have expressed himself or herself if they'd thought about it? That's the problem. It's the problem of uncaused, appropriate, coherent behavior without limits. I sometimes call the creative aspect of language use. Now that's a different problem from another one. How can a finite system characterize an infinite number of expressions? To characterize an expression doesn't mean just to list it. It means to give its form, its meaning, its sound, everything you know about it. How can an infinite amount of information be stored in a finite brain? That's a different question from the question of how you can carry out the creative aspect of language use. It sounds like the same question, and until the 1950s it was thought to be the same question. But once the concept of computability, what's technically called generative procedures, once that was clarified, these two questions separated. And one of them is studyable. The other one's not studyable. That remains the case. So the one that's studyable is the one that has to do with the nature of the information that's stored in your head. Somehow in the language faculty of your brain, which is like an organ of it's kind of like the kidney, as far as we know, an organ of the body. So in the language faculty of the brain, whatever it is, wherever it is, nobody knows exactly, but it's there. The language faculty of the brain has stored in it an infinite amount of information about a particular linguistic system, whichever yours is, whatever mixture it is. On the other hand, there's another question, that is, how do you use it? How do you use it in ways which are appropriate to situations but uncaused by situations, or and uncaused by your internal state? Those turn out to be quite different questions. One of them is investigable, the other is not. The one that you can investigate has led to the modern study of language. The one that you can't investigate is in exactly where Descartes left it. Total mystery. Incidentally, this is not just true of language. It's true of every aspect of psychology and physiology. So suppose you're studying, say, vision. There's a lot of work in the last 50 years on the visual system. And it's all about things that happen between the retina and the striate cortex. So it's about the mechanisms of vision. It's about how stimulation of the retina leads you to see a cube rotating in space. But nobody asks the question, how do you decide to look at a sunset, let's say? That's a question about vision, but it's not a question that can be asked, so nobody bothers asking it. I mean, it's a question, all right, but it's a question that we can ask and just stare at in kind of confusion, not knowing where to go. Because, again, it's a question of appropriate, voluntary action. And those questions are just not within our range of inquiry. Or similarly, suppose you're, say, studying, there's work on, turns out to be extremely hard to explain how to account for the fact that I can, say, reach over here and pick up an apple, let's say. That's a very hard thing to do. It's extremely hard to get a robot to do it. It turns out to be quite complex. The motor actions and coordination and control and so on that are going on, pretty complicated. And there's a very interesting study about how you do it. I mean, it seems easy, just reach over and pick up the apple, but to figure out what you're doing turns out to be extremely complex. And there is a big study, and an interesting study of the mechanisms of motor control and programming and coordination, but nobody studies the question of why I decided to pick up the apple. Why did I pick the apple up and not my watch or something? That's not a question that you can study, and that's a question that's analogous to the question of use of language. And in fact, if you think across the board, that's the way it always goes. When you talk, the things that can be studied are questions about mechanisms, about how knowledge is stored, how internal programming takes place, how one kind of representation, say a mapping, the retinal mapping, can turn into another one, let's say concept of percept of a cube rotating in space. Those things have been subjected to inquiry, and we know a lot about them. But a whole class of other things, of which the use of language is one, they remain where they always were. And remember, those are the ones that were traditionally exciting. Those are the ones that led to the traditional mind-body problem. I'll come back to where the study of what we can study went from there. But first, an aside on the mind-body problem. What happened to that problem? Well, is that problem still around? Well, a lot of people seem to think it's around. So there's a big, there's what's in fact sometimes called an orthodoxy in philosophy, which is that things can be reduced to, the orthodoxy is that philosophical questions about the mind and mental activity and mental events and so on should be reducible to the material world, to something about the physical world, which is supposed to give you a resolution of the mind-body problem. And there are big debates about whether you can do it or you can't do it and so on. These debates are rather curious because the mind-body problem doesn't exist. And it doesn't exist because it was demolished by Isaac Newton 3 centuries ago. Newton didn't have anything to say about the Cartesians had a theory of mind and a theory of body. In fact, science altogether had a theory of body. It was called the mechanical worldview. And it was very commonsensical. The mechanical, it probably is our common sense picture of the world. And that was science. The top scientists of the day, Huygens and others, were trying to develop a mechanical worldview to show that the world is a machine. That was the big job, show that the world's a machine. And then Descartes came, his argument was, well, yeah, the world's a machine, and in fact everything's a machine except the creative aspect of language use and some other things like that, which don't seem to be duplicable by automata. So that's the second substance, that's mind. Well, what happened to that picture? What happened is that Newton showed that nothing is a machine. In fact, that's exactly what he showed, if you think about it. What Newton showed, much to his distress, I should say, and to the distress of everyone else, who thought it was kind of like a reversion to traditional mysticism, is that the entire world is immaterial. The world is governed by immaterial forces, what were in fact called occult forces. Anybody knows, as Newton pointed out, it's an utter absurdity which no one with the slightest scientific, he said philosophical, but I mean scientific understanding could believe that one object can influence another if they're not in contact. That is a total absurdity, and it certainly is a common sense absurdity. It just happens to be true. He showed it was true. Universal gravitation showed that, in fact, what is an utter absurdity is true, and that was quite disturbing. But the effect of it was to show that the world isn't a machine. In fact, nothing's a machine. Even simple terrestrial and planetary motion aren't mechanical. The mechanical world picture was demolished. It's commonly said now, it's common these days in philosophy and elsewhere, to deride theories of the mind as being a ghost in a machine, and we got to exorcise the ghost. But what's forgotten is that Newton exorcised the machine. He left the ghost untouched. He had nothing to say about the theory of mind. He, in fact, assumed that somehow if we ever figured this stuff out, it would incorporate mind. But it was left as a total mystery, and it remains a total mystery. In fact, it's just gotten more mysterious since, as physics has introduced more and more crazy ideas to try to account for what goes on in the world. So there is no notion of material, and there's no notion of physical, and there's no notion of body, and so on. Hence, there cannot be a mind-body problem. What there is just various aspects of the world, and you try to understand them the best you can and unify your understanding as best you can. But I don't think that anyone has formulated a coherent version of the mind-body problem since the 17th century. So it's not at all clear to me, at least, what people are arguing about when they say they think that the mind can be reduced to the body, or they don't think it can, or whatever. Since there's no notion of body, the debate doesn't seem to be about anything. But the problems remain. I mean, the problems of of the mental aspects of the world, they remain. And they remain for the most part unsolved. We can pull out little pieces of them and get insight, like the nature of the mechanisms that underlie infinite knowledge. There we can get a lot of insight. But the main questions about the mental aspects of the world, like, for example, the question of coherent, appropriate, meaningful action, which is apparently uncaused as far as anyone can tell, that problem remains, and it remains completely mysterious. That's aside. Now, back to the part you can study. So now we're at a point where you can resurrect the old problems, but from a new point of view. Look at the way in which infinite knowledge is stored in a finite brain, figure out what the mechanisms are. As you looked closely, it quickly turned out that the things that were thought to be simple are in fact completely not understood, like what's the nature of a river, or how do you form questions, totally not understood. All the information we had about it was just data, that was hints to a person who already knew the answers, and we were trying to figure out the answers. At that point, serious inquiry begins, and it led to an immediate paradox instantly. First thing that happened already by the 1950s is as soon as you started to ask the questions, a flood of data came along, which no one had ever suspected about how sentences are put together. Exactly as happened when people started studying what happens when something rolls down an inclined plane. Turned out that all kind of weird things were happening that no one had ever guessed, like, speed depended on the time, not the distance, and things like that. And here, too, tons of information came around that nobody had ever noticed before, and great effort was made to try to give an accurate description of it, at least, to try to present precise rule systems that would at least assign the right meaning to the right expressions over some sort of an interesting range. Well, it turned out that the effort to do that the one example that you heard is typical. As soon as you start to do it, you find very funny things, and you've got to complicate the rules to account for them. And the rules were getting proliferated all over the place. You take a look at a kind of grammar that was written in the 1950s, thousands of rules for all sorts of different things. And furthermore, they were different for every language. So if you ask how you form a question, it looks, if you give the precise, if you try to lay out the details of what questions look like in English and what they look like in French and what they look like in Chinese and so on, they just look completely different. In fact, if you look at questions in English and relative clauses in English, they look totally different. And in fact, every two things you look at just look completely different. And the rule systems were exploding all over the place, and they were different for every two languages and so on. Well, that's what happened when you tried to achieve what was called descriptive adequacy. Just give an account of the facts, at least, in a precise fashion, without appealing to what is understood, without relying on what is tacitly understood, rather trying to spell it out. Same in the case of dictionaries, I should say. So that's the way. That's the direction you were forced to go as you started paying attention to the facts. On the other hand, it was completely obvious that it can't be correct. The reason it can't be correct is because of the problem of acquisition of knowledge. Children acquire the idea that the problem is overlearning is completely crazy. The problem is how anybody knows anything. If you look at the actual data available to a child, it is so limited and sporadic that to get anything out of it is kind of miraculous. It's like the question how an embryo, on the basis, in fact, very much like the question of how an embryo, given nutrition, can become a chicken, let's say. Well, obviously, the nutrition doesn't tell it how to become a chicken, because a different embryo, given essentially the same nutrition, might become a whale or something. So it can't be in the nutrition, because the nutrition doesn't direct the development. It's got to be something about the embryo that's determining it. And the same is true of the problem of language acquisition. The data is much too sparse to lead to anything. And something very complex and specific is coming out, like what you have in your head, and somehow that's got to be inside you. So it's pretty much the same problem as embryology. In fact, it is the same problem. And the same thing happens for, say, postnatal development. Again, people don't seem to ask much about it, but if you think about it, it's the same kind of question. Like, say, every person within some very substantial range undergoes puberty at roughly a certain age. Okay, how do you do it? I mean, it can't be some instructions from the environment. It's not peer pressure. It's not. Our kids are doing it, I better do it too, or something like that. It's got to. And on the other hand, there's no instructions around. I mean, it's true that if the nutritional level is low enough, so you're practically starving to death, then it won't happen. But within a very substantial range, it's going to happen, and it's going to happen in a very special way. Well, that's postnatal. In fact, it's probably after the period in which language is already settled, but somehow it's got to be internally determined. And in fact, every biologist assumes this. I don't think anybody knows a thing about it, but everyone assumes that it's internally determined and just has to be. And it has to be because there's just no information around that's forcing this specific development to take place. And the same is true of language acquisition and, in fact, everything you look at. So on the one hand, you know that languages have to be basically identical because they must be derived from the fixed internal knowledge. And we're not internally programmed to know English or Spanish, everybody knows that. So there's some fixed internal knowledge which is determining virtually everything about the language. And some details around are making it one language or another, and they've got to be basically the same. On the other hand, when you look at them, they look totally different and so complicated you couldn't possibly learn them from the data around. That was the problem, paradox. To account for the fact that languages can be acquired, you knew that they were going to all turn out to be essentially identical. But when you looked at, and very simple, in fact, because you've got to pick them up on the basis of very restricted data. On the other hand, when you looked at the actual materials, they looked completely diverse, and it did indeed look as if they could vary in every possible way. Well, the answer to that, the way to answer that problem was understood immediately, and it set the task for quite some time. The way to answer it is to try to take the mass of complicated data, like, say, forming questions, and show that it's only superficially complex, that actually if you pursue it deeply enough, you'll find principles that determine how things work, which are hidden. You're not going to see them in the data. And that those principles will interact somehow to yield the complexity of the data, even though the principles are fixed. And the reason why languages will look different is because there's some little variation here and there that make the principles work differently. If you take a very intricate mechanism and you make slight changes in it here and there, the output of what it does can look totally different, even though there's only tiny little changes going on. And that it had to be something like that. So that started a search for principles of computation, basically, and organization and structure, which had the property that if you could find them and you could abstract them from the data, what was left was very simple. In fact, what was left, you hoped, would be something like move anything anywhere. In fact, that's pretty much what turned out to be the case. So move anything anywhere is the right kind of principle. But it's only going to work, to give you examples like what you heard and a million others like them, if you know something about the structure, about the properties of structures that can be formed, and conditions on the way these things can move and so on. So from about 1960, that was the main direction of research, and it kind of converged. It was making progress for 20 years. Around 1980, it did converge in a totally different picture of language. And that's really the first major change in the conception of language in about 2,500 years, I think. This is an old subject. And if you go back to ancient India, there were things like what we call generative grammars, that is, detailed grammars that formed expressions and so on, but of the type of early generative grammar and traditional grammar. The picture that came out around 1980, as all this stuff sort of finally began to fall together, was a very different one. It was a picture that said languages don't have rules at all. The traditional story, what you learn when you pick up a grammar of Spanish, it has a chapter on how to form questions in Spanish, or how to form verb phrases in Spanish. These grammars traditional grammars are construction-based and rule-based. They assume that there are certain constructions, like passive or relative clause or verb phrase and so on, and then there are rules for handling those constructions. That every traditional grammar is like that, and that goes back thousands of years. And early generative grammars were also like that. Like there was a rule for forming relative clauses in English, and it was a very complicated rule. And there was another rule for forming questions in Spanish, and that was a very complicated rule, and so on. And a rule for forming verb phrases in German, and that looked totally different. It was another rule. So these grammars, like traditional ones, were rule-based and construction-based. The picture that finally emerged from what I've been describing assumed that there are no rules at all, and there are no constructions at all. Constructions are just taxonomic artifacts. There is nothing like relative clause or question or verb phrase any more than there's something like terrestrial mammal or household pet. Now, when I say there's nothing like household pet, I don't mean, your cat doesn't exist. What I mean is that household pet is not a biological category, and terrestrial mammal is not a biological category. In fact, neither is tree. It's not a biological category. It's maybe a human category, but it's not a category in the world. Just like rivers are in our human categories, but not things in the world in our sense. Each particular instance of a river is, but that's a different question. That's like your cat exists. So it seems to turn out that the traditional constructions, like verb phrase or passive and relative clause and so on, are just like household pet. They're taxonomic artifacts. They are things that fall together when principles happen to interact in a particular fashion. Then you get these things. But the same principles, very same principles, when they interact in a slightly different fashion, they give you one of the other taxonomic artifacts, but it's the same principles. That's the picture that began to emerge. No constructions, no rules, just very general principles. Well, how do languages differ? Because they're obviously not all the same. Well, the idea was that they differed only in a very narrow, in fact, probably finite, in a clearly finite number of ways. And the ways had to do with what are called parameters, slight points of variation, which are very local. In fact, they're probably localized not only in the lexicon, in the category of words, but even in certain very narrow properties of words, in what are called formal properties of words, like case, like all the stuff you study, in fact, when you study another language, like case and inflection and agreement and so on, or what you do with the WH phrase and things like that. There's a small number of ways in which languages can differ, and they have to do with particular formal properties of certain kinds of words. In fact, if you look even more closely, it seems to turn out that all languages are the same in these properties, but they're just different in how it comes out the mouth. So go back to the example that was given at the beginning of forming questions. In English, you do take this question word and you put it in the front. So you say, what did you see? In Chinese, you leave it where it was. But if you look closely, you find out that English and Chinese give the same interpretations of expressions. So, for example, let's take a slightly more complicated case. If you take a sentence in English like, Mary wants to fix the car with a wrench, let's say, and you want to ask, you didn't hear what she fixed. So you say, what does Mary want to fix with a wrench? And I can say the car, or maybe you didn't hear how she did it, and you ask, how did Mary want to fix the car? And I say, with a wrench. That's okay. And you can do the same in Chinese, even though you leave the words in place. On the other hand, suppose instead of wants to, you had wonders whether to. Okay, slight change. So now we have the sentence, Mary wonders whether to fix the car with a wrench. Okay, and now you didn't hear the car and you ask about it and you say, what does Mary wonder whether to fix with a wrench? Answer, the car. And suppose you do the how case. How does Mary wonder whether to fix the car? And that doesn't work at all. That you're asking something about wondering. You're not asking about fixing. So the question can't be, how does Mary wonder whether to fix the car? Answer, with the wrench. That doesn't work. Well, the fact is it also doesn't work in Chinese, even though you leave the WH, the question word, down below. So apparently in Chinese they're doing exactly the same thing we are. And something is blocking moving the question word to the front, and we have a good idea what it is. But in Chinese, they're just doing it in their heads. It's not coming out the mouth. Okay, so they're running through the same computation, apparently, but only a certain piece of it is getting articulated. Whereas in English, the computation itself is getting articulated. But in fact, Chinese and English look exactly alike. And as far as we know, every language looks exactly alike, except for the fact that languages differ in which piece comes out the mouth. Well, that's a case where something comes out in English and doesn't come out in Chinese. It works the other way, too, as you can imagine. So if you've studied, say, Latin or Greek or German, you had to spend a lot of time learning about inflections, case endings and nominative and accusative and all that kind of stuff. Chinese you don't hear them at all. English, you barely hear them. You hear them for pronouns, but nothing else. Like, I saw John, and John saw Mary, and Mary saw John. In Latin, one would be nominative and the other accusative, and the opposite. But in English, they sound the same. On the other hand, there's extremely good evidence by now that English has exactly the same case system as Latin, except it just doesn't come out the mouth. You can see the effects of it. When you begin to figure out how case systems really work and the consequences they have for interpretation of sentences and what is a sentence and so on, you find you get exactly the same things in English you get in Latin, almost exactly, not quite exactly. And the same in Sanskrit, and the same in Finnish, which has even more cases, and the same in German, and so on and so forth. So it looks as if English and Chinese have all the cases. It's just that they're not coming out the mouth. We're doing the same computations in our heads, but it isn't getting articulated. And in fact, it seems that an awful lot of the difference among languages just has to do with which properties are getting articulated. It looks as if the computations are all the same. Like in all languages, you have a collection of building blocks, things like words, and you have a couple of very simple operations for putting them together, and they meet very general conditions, and the languages seem to differ wildly because different things are coming out the mouth. But in fact, it's the same computation. So if a Martian, say, was looking at us, the Martian would assume that all humans speak exactly the same language with extremely trivial differences among them. Pretty much the way we assume that take one species of frog, we say, look, they're all the same, although the frogs may well think they're very different from one another, and in fact be interested in the differences, and we're interested in, of course, in the differences among humans, not in what's identical about them. That we just kind of take for granted. But if you look from the point of view of a scientist, like a rational Martian looking at us the way we look at fruit flies or something, we would probably look essentially identical, with extremely slight divergences. And in the case of this aspect of language, that part is now becoming clearer. I wouldn't argue it's totally understood, but it's certainly becoming clearer. It's becoming reasonably clear that there is a fixed set of principles that determine a unique kind of computation for all languages, so they're basically all identical, and that the apparent differences between them have to do with things like what comes out the mouth, and it seems to vary almost entirely in the so-called formal properties, things like inflection or question word or something like that, not in other things. In fact, even it's looked for a long time as if the ordering of languages was very different. So English, it's like subject, verb, object. In Japanese, it's subject, object, verb. English, it's preposition, noun phrase, in the room. In Japanese, it's noun phrase, preposition, room, in. In fact, Japanese looks like the mirror image of English, virtually. So it looked as if they just differ. There's a so-called parametric difference that says English goes to the right and Japanese goes to the left. It turns out that even that isn't obvious. There's a new book that's just come out by a very good linguist, Richie Kane, MIT Press just published it, who argues that, in fact, they're all identical even here. And there's some other tiny difference that makes languages look as if they have different orders. And that's not proven, but it's, he's got good evidence, and I wouldn't be at all surprised if it does come out to be right. The more you look, the less languages seem to differ from one another. And notice that this has been achieved without losing the descriptive adequacy. Quite the contrary. The descriptions are much closer to correct than they ever were. And furthermore, they're far more comprehensive, because one of the things that's happened through this period is that every time a new theoretical insight came along about how to organize the system, it immediately stimulated new questions, empirical questions, which then came up with totally new data, which nobody had ever guessed at before, like these things about Chinese. Nobody ever noticed them until about 10 years ago. That it works like English in the interpretations. Well, that brings us pretty close to where we are now. This so-called principles and parameters approach is the first legitimate theory of language ever. It's the first theory that at least offers a way. The details aren't by any means all known, but the picture is not implausible and to some extent understood. It's the kind of theory which allows an answer to the question, how does anybody know a language? It's the first theory that ever allowed an answer to that question. And the answer would be, well, you just have to figure out which things are coming out the mouth. And that's fairly straightforward. Like you hear the cases or you don't hear the cases. Or you hear the question word in front or you don't hear it in front. So it's kind of as if the child comes to the language with the whole story in place, just like undergoing puberty is already in place, or growing arms, not wings or something. It's in place. That's part of the internal instructions. But you've got some things that aren't totally in place. So you have a kind of questionnaire, like finite number of questions. Question 1, do I pronounce the cases or don't I pronounce the cases? Okay. And that's an easy one to answer. You hear it pretty fast. Do I put the question word in front or do I leave it in place? That's an easy one to answer. Computations go on the same way, and they have intricate results, but you know which way you do it. And if you have, let's say, whatever it is, 83 questions like that, you can kind of check off the answers, and once the answers are checked, then the whole system works. Okay, something like that looks like the right picture. Incidentally, I've left out a huge piece of it. How do you know what sound goes with what meaning in the case of words? So how do you know that tree is tree and not baum? That, of course, you have to learn. Like, that's arbitrary. But that's pretty simple. If the whole concept tree, with all of its richness, like river and city and everything else, if that's all in place, and the range of possible sounds is almost entirely in place, then about all you have to learn is how they're linked. And again, that's pretty simple, and it better be pretty simple, because we know that children are learning words at the rate of about 1 an hour during the peak periods of language development, about 2 to 6. And to say that children are learning words at a rate of about 1 an hour, and you notice that to learn a word means to know everything about the word river or water, and I just barely touched on the complexities of it. If you're learning that kind of thing at 1 an hour, you're learning it on 1 exposure, no more than that. So 1 exposure to the word must be sufficient to put in place all of this wealth of information, and therefore it obviously all has to be there. And the only thing you have to be learning is, how does this link between sound and meaning goes? So one big piece of language learning is that kind of thing. Another piece is answering these questions, and a few other things. But that ought to be enough to put the language in place. So this is it's probably the wrong theory, because every theory anybody ever has always turns out to be the wrong theory. But it's the right kind of theory. It's the right kind of theory for language for the first time ever, and indeed the right kind of theory for some aspect of cognition, of the nature of our knowledge and understanding, also for the first time ever. Maybe for the only time ever, because nobody knows how to ask these questions in other areas. But notice that once you've got the right kind of theory, I'll end with this, bringing us up to the present, then new questions arise. The question that comes up is basically, to put it sort of metaphorically, how perfect a system is language? Notice that the language faculty is sitting there in the head somehow, in the mind, where we don't know where or how in the brain, but somewhere in the brain. There's this language faculty. It's got external conditions that it has to meet. Like the language faculty has to interact with the sensory motor system. Okay? Like you have to be able to, it's got to get the muscles of the throat and mouth to work. It has to link up with the perceptual system. It also has to link up with whatever systems there are that get you to do things with language, like talking about rivers or asking questions or telling jokes or whatever. Whatever you do with language is some sort of systems of the mind, and the language system has to link up with those. So in fact, there's a whole set of external conditions on the language faculty. And it has to provide instruction somehow. An expression of a language, like, Mary wanted to fix the car with a wrench. That instruction, as it's computed in your head, that object, as it's computed in your head, has to provide instructions to the articulatory system, the perceptual system, the action systems, the referring systems, and so on, what are sometimes called intentional systems. It has to provide instructions to all those things, which is what enables you to use language. Notice we're not getting to the hard question. How do you use it? Just what kind of instructions are there, and how do they interact? That's the part we can study. Well, those external conditions we don't have really good understanding of, but we have a ton of data about. So there's a ton of data about the way the articulatory system works and the perceptual system works and the intentional system. Nobody understands very much about the use of language, but you know a lot about what sentence means what and how it's used in particular circumstances. You're flooded with data about that. And that mass of data, even with limited understanding, imposes very strong empirical conditions on what the language faculty must be like. Well, the question that you can now raise for the first time is, how well does the language faculty meet those external conditions? Does it meet it the way a really smart engineer would have designed it, or does it meet it in a crummy way? That's the question. So how perfect is language in the sense of, if you just look at the external conditions and you ask what's an optimal solution to those external conditions, how closely does language approximate it? Well, apparently turns out remarkably closely. As more on this work of the last few years, in fact, a lot of it just coming into publication, there's more and more work coming along which seems to indicate that language is very close to a perfect solution to this problem. Now, that has a definite meaning. I'm sort of leaving it metaphorical, but it has quite a definite meaning. It means, and if we had time I could spell it out, but one aspect of this is it appears to turn out that the computational procedures of language have to be, that they meet certain optimality conditions. Meaning if you start with a bunch of words and you're trying to form an expression, you must do it by the most optimal means. And some other means of forming an expression, which would give you something meaningful, is just blocked if there's a more optimal computation. So there's just some things you just can't think because there's a more optimal way of constructing an expression from the same words, things like that. These are sometimes called economy conditions on computation, leave you with the following picture of language. The computational system, which has its fixed principles, not only produces sounds with meanings, but does it in an optimal fashion. And any other way of doing it is blocked because it's not optimal, which means that there are some expressions that can't mean what they ought to mean or can't be said because something else is blocking them. Now, that property of language is pretty remarkable, if it's true, and it looks like it's true. A lot of things can be explained that way. It's remarkable for a number of reasons. One reason is you simply do not find things like this in the organic world. The organic world is a very messy affair. That which is very lucky. I mean, the reason, say, why if you're hit over the head with a crowbar, you can continue to function very often and even go back the way you were. Whereas if you hit a computer with a crowbar, it's finished forever. The reason is that the biological world is a very messy affair. You've got a lot of redundancy built in, and a lot of alternative pathways, and a lot of crummy ways of doing things, and so on and so forth. So therefore, if something goes wrong, something else may go right. The inorganic world isn't like that. It's got to be, you take an atom, let's say, and you change something, it's some totally different thing. Or if you take a machine and you pull out one element, say one chip, the thing is dead. It has no ways of compensating. The biological world, the biological world is also a mess because of the way biological organisms develop. They just evolve under extremely messy conditions. The way many biologists put it is evolution's a tinkerer. It sort of does the best it can with rather rotten conditions. which is one of the reasons why, contrary to sort of Reader's Digest style of biology, every biologist knows that organisms are very badly designed. From an engineering point of view, they're usually extremely badly designed. This is something that all of us know from our own experience. Everybody has back problems. And the reason you have back, in fact, that apparently all vertebrates do. I mean, you can't ask a cow, does your back hurt? But it seems that cows have the same back problems we have. Doesn't even seem to have to do with upright posture. And probably all large vertebrates, some neurophysiologists believe everything back to the shark. The shark's the last well-designed object. And this is a big problem. People suffer from it. And the reason is that the spine is just extremely badly designed. From an engineering point of view, it's a wreck. And in fact, nowadays when people do spine, I had a big spine operation a couple of years ago. They don't even do anything. The blood clot that forms turns out to be about as good as the original disc. So there's nothing to do. You just sort of let it grow back together. And this is true of just about every system of the body. Let's say, we would be a lot better off and be able to save ourselves from a lot of saber-toothed tigers hundreds of thousands of years ago if we had an eye in the back of the head, let's say. But we don't, We have only eyes in the front, and rabbits have them on the side. But there's just a lot of things that would be very useful that aren't around. For example, it would be very useful to have wheels, because then you could go really fast down flat places. But organisms don't have wheels. There's a lot of things they just do the kinds of things they can do, and it's usually a mess. The inorganic world, for some unexplained reason, turns out to be completely different, or at least everyone assumes that it is. The driving intuition of, say, physicists and chemists is that somehow it's all going to come out extremely simple. And if you have, say, numbers like 7 around, you figure you must have made some mistake, because the only real numbers are things like 2 and 3, so it's really got to be 8, 2 cubed or something. And that's the driving intuition behind almost all the study of the inorganic world, and it has been remarkably successful, so there's probably something to it. Why, nobody knows, but it seems to be true. And language is very much like that, it seems. Again, this could be an artifact. Maybe we're fooling ourselves. That's always possible. But it looks as if language is very much like the kind of thing you find in the inorganic world. Well, that's kind of curious, because it's the most complicated thing, apparently, that the organic world produced. So why does it look like that? In fact, really, right at its core, you already have this property. So language is a system which is technically called a system of discrete infinity. Infinity means, say, and it's a very simple idea. I mean, say take words. You can have a 6-word sentence. You can have a 7-word sentence, but you can't have a 6.5-word sentence, right? And every aspect of language is like that, and we sort of take it for granted. But it's a strange fact, because there's essentially nothing in the organic world that meets the condition of discrete infinity. You have plenty of continuous systems. Like if you look at neural maps, they vary continuously all over the place. You have plenty of finite systems. Like you look at ape calls. Some particular ape might have 49 calls or something. But systems which are both discrete and infinite are very rare. In fact, I think the only place you find anything like it in the biological world is when you get down to the level of big molecules, and then you're back in the inorganic world. So you look at DNA, well, there's a certain sense in which it's discrete infinity, but that's the level where you're really talking about biochemistry. When you go into actual biological organisms, you seem to move directly to continuity and finiteness, except for this. Furthermore, this seems to have other properties that are rare, if not non-existent, in the biological world. Furthermore, if the economy conditions are real, and they seem to be, those of you who know anything about computability will recognize right off that if you introduce economy considerations, you say one computation is blocked if there's another more economical one, you introduce huge computability problems, unsolvable computability problems. So the question is, how does anybody know it if the problems are unsolvable? Like, how do you know that this derivation is going to block another one, which turns out very quickly to be a problem of a very high level of computational complexity, way beyond what's solvable? So if it's true, what it means is that large parts of language must simply be unusable, because they will involve computability problems that can't be solved. Now, in itself, that's not a surprising conclusion because we know it's true. We know that large parts of language are just unusable. In fact, a good part of the psychological work, psycholinguistics, the study of how language is processed and so on, picks as its data things that are unusable. Things like garden path sentences, for those of you who know this kind of stuff. Those are all selections from parts of language that are unusable, and they're interesting to test for that reason. They give you interesting things about processing or learn from the part. These can be quite simple sentences. They just can't be understood. So we know that large and scattered parts of language are completely unusable. That shouldn't bother anyone who thinks about language from the point of view of real biology, not pop biology. In pop biology, everything's supposed to be usable and well adapted, remember. But in the real world, everything is a mess and nothing works at all. It just works well enough so you don't die. That's got to work well enough so you can reproduce. If it does that, then you go on. But nothing has to be usable, and most things aren't. So the fact that language isn't, for large parts of languages aren't usable, that's not a problem in itself. But it does raise an extremely interesting question, hard question, right at the horizon now. You can formulate it, but can't deal with it. Can we demonstrate that the parts of language that are technically uncomputable are the part that in fact are unusable? That's a hard question. You can formulate it, but nobody knows how to study it. Well, all of these problems take us right to the present, and they raise very interesting. A lot of people think they're kind of paradoxes. I don't know if they're paradoxes or not, but they're certainly surprising. It seems to turn out that the properties of language that we can study, the parts that we can study, just don't look like the organic world at all. They seem to look a lot like the inorganic world for very mysterious reasons. And they have these strange properties of computation that you simply, not only don't you find in the organic world, but you can't, a lot of it isn't even computable. Well, that's the part of language we can study. What about the part we can't study? Like the part that led to the traditional mind-body problem, no longer formulable as far as I can see because we have no notion of body. How do you actually use language in the ways that we do when we talk to each other normally, the ways that are appropriate to situations not caused by internal states or external events, coherent, intelligible to others, with all those properties? That remains, as it has always been, a complete mystery. And why it remains a mystery is also a mystery. Just notice that the same is true across the board. It's true of the study of vision. It's true of the study of motor mechanisms. It's true of every aspect of psychology and physiology. There is that mysterious core, which is just the questions that we're humanly interested in for the most part, in which you can only stare at puzzlement. That may reflect other aspects of human cognitive capacity. May mean that they're not the kinds of questions we're designed to answer, which could be, or there could be some other reason, but anyhow, that's where things stand at the moment.